Hello and welcome to a new video on IGCSE Classified Physics Paper 2. In this video, we shall be discussing the properties of alpha, beta, and gamma. So to begin with, which role gives the properties of the radiation from radioactive materials? So we have three types of radiation. We have alpha, beta, and gamma. So let's assume that we have a gang here, a gang of fighters or whatever. How would each of these interact with alpha, beta, and gamma? So alpha is a fighter. It's a thug, a bully. Alpha would keep fighting with these gang members. And as a result, it doesn't really go too far. Gamma, on the other hand, would just walk past them, laying low, keeping its head down. It would not interact with any of them, and thus it has the ability to move very great distances. Beta, on the other hand, is somewhere in the middle. So it interacts a little bit and it penetrates better than alpha. So the fighting here is meant to discuss ionization. It's meant to describe what we call ionization. So alpha is really great at ionization. Gamma, on the other hand, is really great at penetration. Beta is sort of the middleman. It's average in both. So if you were to compare the three, alpha is the best ionizer, beta is medium, gamma is the worst ionizer. On the other hand, gamma is the best penetrator, beta again is medium, and alpha is the worst penetrator. So the most highly ionizing would be alpha, and the most penetrating would be gamma. So C would be the correct choice in this case. Like we said, alpha is the most ionizing, so it's more highly ionizing than gamma. Fast-moving electrons, this would be beta, not alpha. Electromagnetic radiation, this actually would be gamma, not alpha as well. And it is more penetrating than beta. This is also incorrect. It's the least penetrating of all of them. It's the most ionizing and the least penetrating. So C is the correct choice. Alpha, beta, and gamma are emitted by radioactive substances. Alpha consists of charged particles and is the most highly ionizing. We said this is correct. Beta consists of charged particles and is the most penetrating. Beta is not the most anything. Beta is average in everything. Beta consists of uncharged particles and is the least ionizing. It's also not the least anything. Like we said, beta is in the middle, and it's actually not uncharged. It's actually charged. Beta is sort of like an electron, so it has one negative charge. Gamma consists of uncharged particles and is the least penetrating. No, it's the most penetrating. So A is the correct choice. Which row describes the nature and a property of all beta particles? Like we said, beta is similar to an electron, has zero mass and -1 charge. So the nature is an electron. A helium nucleus is the same as an alpha particle. It has two positively charged protons and two neutrons, giving it a mass number of 4. So for beta, we're going for electrons. Can it travel through vacuum or is it stopped by a thin sheet of paper? So alpha is stopped by a thin sheet of paper. Beta cannot, beta can travel through a thin sheet of paper. And beta can travel through vacuum since electrons can travel through vacuum. So A is the correct choice in this case. Which particle has a negative charge? An electron, of course, or a beta particle. Excuse me, I misrepresented. An electron or a beta particle. So the correct choice here is B. Which statement about alpha particles and beta particles is correct? So alpha particles are less ionizing than beta. This is incorrect, of course. Alpha is the most ionizing. Alpha particles are more penetrating than beta. Again, remember, alpha is the best ionizer and the worst penetrator. Alpha particles have greater mass than beta. This is correct. We said alpha has 2 neutrons, 2 protons. Beta has no neutrons or protons, just a negative electric charge. So beta is almost zero mass. Not zero, but like it has a 1/1,000,000th of the mass of alpha, actually. Alpha has the same charge as beta. This is incorrect. Alpha is positive and beta is negative. So C is the correct choice in this case. The table compares the penetrating abilities and ionizing effects of alpha and gamma. We said alpha is the most ionizing, and alpha would be the least penetrating as well. Not gamma is the most penetrating. So the most ionizing is definitely equal to the least penetrating. So A is the correct choice in this case. Applications of alpha, beta, and gamma. The arrangement shown is used to check whether the flour inside the cardboard packet is above a certain level. If it's above the level, the flour absorbs the radiation from the source so that it doesn't reach the detector. Which type of radiation is suitable to use? So in general, the radioactive source is expected to reach the detector. So we want something that in general can pass through the cardboard packet. So alpha wouldn't work here. Why would it not work? Because alpha would not be able to pass through the first layer here, through the first cardboard packet. Alpha cannot pass through cardboard to begin with, so it does not work in this case. However, once a certain layer of flour reaches a certain level, so once flour reaches this height, for example, we want this source to not be able to pass through the flour so that the detector can detect a change. It stops receiving the radioactive emissions and it sounds an alarm or it stops an operation or whatever. So the problem with gamma is that gamma can pass through flour. Gamma is very penetrating. So that would not work either. The only particle that would work here is beta, because in the normal circumstance, beta can pass through the cardboard and go from the source to the detector, so it would work. But once we add in the flour, beta will not be able to pass and the detector will sense that something is different and it will sound an alarm or it will just stop packing the packet. So B would be the correct choice in this case. Radioactive source S emits alpha, beta, and gamma. A detector is placed 5 centimeters away from S. A thin sheet of paper is placed as shown in the diagram. Which emissions from the source can be detected? So a thin sheet of paper would stop alpha. Alpha is very weak in terms of penetration. So alpha would not reach the detector. So it can read, so the detector can read beta and gamma, but it would not be able to read any alpha particles because of the thin sheet of paper. So C is the correct choice here. A radioactive source emits 3 types of radiation, R, S, and T. The diagram shows an experiment set up to study the penetrating properties of R, S, and T. Which types of radiation are R, S, and T? So we said that alpha is the least penetrating, so we expect R to be alpha. Gamma is the most penetrating, so S is gamma, and beta is average, so the middle ground is T, and therefore beta is equal to T. So we're going to go with beta for T, and gamma for S, and alpha for R. Hence, B is the correct choice in this case. The diagram shows the paths of 3 different types of radiations, X, Y, and Z. Again, in this case, Y is the least penetrating, right? So Y would be alpha. X is medium, so X would be beta. And Z is the most penetrating, so Z would be gamma. So for Z, we have gamma, but for Y, we have alpha. So this is incorrect. And X is beta, so B is the correct choice. Now we move on to questions that have to do with safety of handling radioactive material. Radioactive materials should be handled carefully. Which safety precaution does not reduce the risk to people using radioactive material? So which of these would be useless in other terms? Keeping the material a long distance from people? No, this is useful actually, so we want this. Keeping the material at a low temperature? This has nothing to do with what we're saying. Using lead screening, this would protect people. Using the material for a short time, this would protect people. So long distance, short time, and using protective lead. These would all protect us from radioactive materials. However, low temperature has nothing to do with the issue. Hence, B is the correct answer here. A hospital doctor is using a source of gamma rays for medical treatment. Each diagram shows a view from above of the treatment room. Which diagram shows the best way to protect the doctor and the staff in the corridor from the gamma rays? So we have the doctor. Of course, in A, the doctor is very close to the source. This doesn't make any sense. In B, the doctor is outside, and we have sort of a room where the source is inside and the doctor is outside. So this is good. However, in C, remember this shaded area here is dense concrete. Concrete is a very preventive material. It's very thick, so it would protect the doctor. So we definitely want the doctor to be outside the dense concrete. So C would also be incorrect because we want the concrete to block the source from the doctor. So it's either B or D. Which of them would be better? Or should we have B or should we have D? Of course, it's better to have the source further away from the doctor. This line of sight here is problematic because in this case, the source can just go through the wood and affect the doctor. We want the source to not be able to go through the wood. We want the source to be able to go through the dense concrete in order to protect the doctor. So D is the best arrangement in terms of health. Which is the most effective precaution to reduce the risk when handling, storing, or using a radioactive source that emits gamma rays? Handle the source for the least possible time. That's good. Fire extinguisher, not really. Low temperature, not really. Plastic safety goggles wouldn't really do anything. So lead, we need something like lead or concrete. So these are all incorrect, and the least possible time would be the most effective. Radioactive materials must be handled in a safe way. What is not a safety procedure? Exposure time. No, exposure time is good. Using tongs and maintaining a distance. Tongs are like very long scissors that you can use to pick up the material to keep a distance. So this is also a good strategy. Protective clothing, of course, would be good. However, cardboard boxes are completely inefficient. They would not really do anything to keep us safe. So B is the correct choice in this case. Next, we move on to Rutherford's experiment. Rutherford's experiment is the experiment that taught us about what an atom looks like and how the nucleus is in the center of the atom and it occupies a very small space. So if you have a football field like this and you have like a soccer ball, this is the approximate relative size of the nucleus and the actual atom. So the nucleus occupies a very small amount or portion of the total size of the atom. So let's move on to the questions. A very important experiment increased scientists' understanding of the structure of matter. In the experiment, particles scattered as they passed through a thin metal foil. Which particles were used and to which conclusion did the experiment lead? So this is Rutherford's experiment. Basically what happened was they had thin gold foil. So they had like a layer of thin gold foil. And they passed alpha particles through the foil. And what they saw was that most of the alpha particles were able to move to the other side. Most of them were able to move to the other side. Some very few were deflected in this direction, and also very few were deflected backwards. What did this experiment tell us in terms of the structure of matter? It told us that we have a very big atom with a very small nucleus, and that the nucleus is positively charged. So when we have alpha particles moving through the atom, nothing happens. However, as they get a bit closer to the nucleus, they deflect, they repel, because positive and positive repel. And for the very, very few that actually hit the nucleus head-on, they are reflected backwards. So this is why some reading was detected here, very little reading was detected here, and most of the readings were detected in this region because any alpha particle that did not really pass close to the nucleus just moved on to the other side and was detected inside the red box. So we used alpha particles, and it says that, or the conclusion is that atoms have a very small nucleus. The nucleus occupies a very small space inside the atom. So B would be the correct choice in this case. Which diagram represents an experiment that provided evidence for the nuclear atom? Like we said, this experiment involved alpha particles because these were the ones that were repelled. So definitely not beta particles. And are the alpha particles attracted to the nucleus? Do they bend towards the nucleus or do they bend away? Of course, they bend away because positive and positive repel. We said that the nucleus is positively charged and the alpha is positively charged. So it definitely repels away. So C is the correct choice in this case. When a source of alpha particles is directed towards a thin metal foil, they become scattered. Which observation of this experiment provides evidence for a small charged nucleus? So a small proportion of the alpha particles come straight back from the foil towards the source. This is actually what led us to believe that the nucleus has a very small size. Because like we said, if this is the nucleus and this is the atom, most of the alpha particles are going to pass through, but only very rarely will an alpha particle hit the nucleus and move back. So this tells us that the nucleus occupies a very small space of the atom. Hence, in this case, A would be the correct choice. A very important experiment improved scientists' understanding of the structure of matter. The experiment involved alpha particles being fired at a thin gold foil. What happened, excuse me, all the alpha particles were absorbed by the nuclei of the gold atoms. Of course, this is incorrect. All the alpha particles were unaffected, not all of them, most of them, but some of them were affected. They were reflected back. Some of the alpha particles were attracted by the neutrons. Neutrons would never attract alpha particles because neutrons do not have a charge, so they do not attract anything. Some of the alpha particles were repelled by the protons in the nuclei. This makes a lot of sense. So D is the correct choice in this case. In the diagram, the circle represents an atom, not to scale. With the nucleus at its center, a particle is emitted by a radioactive source and approaches the nucleus of the atom. The curved arrow shows the path of the particle. Like we said, this is an alpha particle, and the charge of the particle is positive, which is why it is repelled by the nucleus. So B is the correct choice in this case. Finally, we'll investigate the effect of electric and magnetic fields on alpha, beta, and gamma. Which row describes the behavior of gamma rays in an electric field and in a magnetic field? So you should know that if something is charged, it will be affected by electric fields and magnetic fields as well. However, gamma rays are not charged. They do not have a positive or a negative charge. Therefore, they will have absolutely no effect in an electric field or a magnetic field. They are undeflected in both cases. Hence, D is the correct choice here. And as alpha particles pass through the electric field between two charged plates, they are deflected downwards. What happens to gamma rays passing through the same electric field? We just said that gamma rays are not affected at all because they don't have charge. Hence, C is the correct choice. Excuse me, I'm sorry. The diagram shows emissions from a source passing into the electric field between two charged plates. What is emitted by this source? So for the arrow that passes straight through, this must be gamma because it's not affected at all. And then the other arrow is attracted to the negative. So it must be something that is positively charged. Hence, it must be alpha. So in this case, we have alpha and gamma. Hence, C is the correct choice. Alpha particles and gamma rays only. The radiation from a radioactive source passes between two metal plates and is deflected as shown in the diagram. Between the plates, there is a magnetic field directed into the plane of the paper, as indicated by the crosses. Only one type of radiation is present. Which situation is possible? The source emits alpha particles and there is an upwards electric field between the plates. So if the electric field here is upwards, if the electric field is in this direction, this tells us that we have positive at the bottom and negative above, because the electric field goes from positive to negative. So in this case, if this was an alpha source, if these were alpha particles, they would actually be deflected upwards because they would be attracted to the negative. So this scenario here is not possible. The source emits alpha particles and there is no electric field between the plates. So if there's no electric field, then the alpha would not be attracted to the downwards plate. It would just pass through, or it would have any other deflection that has nothing to do with the electric field itself. So the fact that there is no electric field means that alpha cannot be deflected downwards, and that would not make sense either. The source emits beta particles and there is an upwards electric field between the plates. Again, upwards means that we have positive here and negative here. And beta particles would definitely be attracted to the positive, so that would make sense. So C might be correct, probably is. The source emits gamma radiation and there is a downwards electric field. Of course, gamma is not affected by any electric field, so it would not be deflected downwards or upwards. Hence, C is the only correct choice in this case. And C is the correct answer. A beta particle enters a uniform magnetic field directed out of the page. In which direction is the beta particle deflected? So in this case, we have to use Fleming's left-hand rule. Of course, we have three fingers. The first finger is the field. So the thumb is the thrust or the force. The first finger is the field and the second finger is the current. So since beta is negative and we deal with conventional current, the current is to the left. So our middle finger should be pointed to the left. And the direction of the field is out of the page. So your first finger should be pointed towards yourself. So if you have a current to the left and your first finger is pointing out of the page or towards yourself, the thumb is definitely up. This is the only way it would work. Remember, this is not pointing downwards. This is more like towards outside of the page. So something like this. This would be a better representation. So this is the second finger. This is your first finger. And this is your thumb. Excuse me. So the thumb would be necessarily pointing upwards. However, therefore, it's towards the top of the page. So A is the correct choice here. An alpha particle enters a uniform magnetic field directed out of the page. So alpha is positive, hence the middle finger here is pointing up. And the magnetic field is going out, so your first finger is pointing towards yourself or away from the page. Therefore, you're going to find that your thumb is necessarily pointing to the right. So this is the second finger. This is the first finger. So therefore, the thumb must be pointing to the right. So the answer is to the right. D is the correct choice. Emissions X and Y from radioactive material are passed through a magnetic field. The diagram shows the direction of the emissions, the direction of the magnetic field, and the effect on the emissions. Which type of emission is X and which type of emission is Y? Of course, we know that gamma is not a possibility here because gamma would actually just pass through without any effect. So it's definitely not B and definitely not D. So which of these is correct? Is it A or is it C? So there are two things you need to take into account here: the direction and the extent of the deflection. Alpha particles are very heavy. Alpha particles have a mass number of 4. Beta particles have almost 0 mass number and a negative charge. So even without doing the left-hand rule, you should be able to understand that the alpha is not deflected that much because it's very heavy. So this is alpha. And beta is very easily deflected because it's very light. So this is beta. So the correct answer, without even doing the left-hand rule, the correct answer is A, just because of the weight of alpha and beta. But let's also do the left-hand rule to confirm. So the magnetic field is into the page. So your first finger is into the page. Or let me draw it better. Let me draw it at an angle. This is into the page like this. And the deflection is up. Let's say for X, the deflection is up. So your thumb needs to be up. So if you have the first finger into the page, like a traditional gun, using your left hand, the first finger is into the page and the thumb is up. Excuse me. So the second finger is automatically directed towards the right. The middle finger is automatically directed towards the right. And the middle finger represents the current. So the conventional current, the positive charges are moving to the right. So therefore, this charge here is the alpha. And the charge that moves to the left here would have to be the beta. So anyway, in this case, A is the correct choice. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.